In an earlier video, Calculus 339, I have shown how to generate the points for the ellipse by using two foci. The link for this video is in the description section. In this video, instead of using two foci to generate the points for the ellipse, we will use one focus and a directrix. This is called the directrix, this is called the focus. And we will generate the points for this ellipse, and then we've also shown that the polar equation for this ellipse is R equal to EG, and dividing by 1 minus E cosine of theta. And now I'm going to show how to generate the points for an ellipse in the polar coordinate system. And so first, let F be a fixed point, and we'll call it the focus. And then let D be a fixed line, and we'll call it the directrix in the plane. And then let E, which is the eccentricity, be a positive constant between 0 and 1. So E is a number between 0 and 1. And then the set of all points in the plane such that the ratio of the distance from P to F and the distance from P to the directrix is equal to E. Then this set of points will form an ellipse. And so first, let's go ahead and fix and pick F, so that F be at the pole. And then D, pick any fixed line. So in this case, I chose the line x equal to -8. And then next, pick the constant E eccentricity between 0 and 1. So I chose 0.6. Next, we want to find all points such that the distance from the point to F, which is the focus, dividing by the distance from the point to the directrix is equal to E. In this case, is equal to 0.6. And now let's look at these 4 points. So I have point A, B, C, D. And now let's take a look at point C. So now let's take a look at point C and calculate the distance from here to here and the distance from here to the directrix. Point C is located at 0, 4.8. The distance from here to here, from C to the focus, will be 4.8. The distance from C to the directrix will be 8. The distance from C to F dividing by C to the directrix will be 0.6, which is E. And that's what we want. We want all points such that the ratio is equal to E. And now let's look at point D, which is the same thing. Look at this point D right here, which is located at the point 0, -4.8. So the distance from here to here, from D to the focus, is 4.8. And then the distance from the focus to the directrix is 8. So 4.8 dividing by 8 is 0.6. And now look at this point, A. The distance from this point to the focus to F is 12. The distance from this point A to the directrix is 20. So 12 dividing by 20 is 0.6, which is E. And then now let's look at this point B. The distance from B to F is 3. And then the distance from B to the directrix is 5. 3 dividing by 5 is 0.6. And that's what we want to find. We want to find all points such that the ratio from the point of the ratio of the distance from the point to F dividing and the distance from the point to the directrix is equal to 0.6. And here we found 4 points, and here the rest of them. So all of these points, take this point, the distance from this point to F dividing by the distance from this point to the directrix will be 0.6. And so that's how we generate the ellipse. So once again, to generate the points with this ellipse right here, first pick the point, call it the focus, and here we picked it at 0, 0 at the pole. And then next, pick a vertical line that is to the left of the pole or to the right of the pole. In this case, we picked a vertical line to the left of the pole. And then next pick an eccentricity number between 0 and 1, since we want an ellipse. And then in this case, we picked a 0.6. And then next find all points such that this ratio is equal to E. And then we have the ellipse. And now let's find the polar equation for this ellipse. So let F be the point at the pole. Let D be the distance from the pole to this vertical directrix. The equation for this vertical directrix will be x equal to negative d, since the distance from here to here is d. And now let the polar point P r theta be a point on the ellipse. Since P is on the ellipse, that the length of the segment from P to F dividing by the length of the segment from P to R must equal to E. E is a constant between 0 and 1. We call it the eccentricity. This polar point is r theta. Therefore, the angle from here to here will be theta. The distance from here to here will be r. And now look at the right triangle PNF. PNF. This angle is theta, Therefore, this angle will be 180 degrees minus theta, or pi minus theta. The cosine of this angle will be the segment NF, length of segment NF, dividing by the length of segment PF, or FP. So we have cosine pi minus theta is equal to this. From trigonometry, we have cosine of pi minus theta is negative cosine of theta. Therefore, we have negative cosine of theta equal to the length of segment NF dividing by the length of segment FP. The length of segment PF or FP is R, since this is the polar point R theta. So we have NF is equal to negative cosine of theta times the length of segment FP, but the length of segment FP is R, so we get negative cosine of theta. The distance from P to R is the same as the distance from N to D. But the length of ND is be the length of FD minus the length of NF. FD is the distance from the pole to the directrix, and we call that distance D. And then minus NF, which is negative R cosine of theta. So we end up with PR is D plus R cosine of theta. Earlier we had PF dividing by PR is E. PF, that's the length of the segment from P to F, which is R. PR is D plus R cosine of theta. Multiply both sides by D plus R cosine of theta. Move this term to the left side. Factor out the common factor R. Divide both sides by 1 minus E cosine of theta. And we have the equation R equal to ED dividing by 1 minus E cosine of theta. E, again, is the distance from P to F dividing by the distance from P to the directrix, and where E is a constant between 0 and 1. D is the distance from the pole to the directrix. Once again, the polar equation for this ellipse is R equal to ED divided by 1 minus E cosine of theta. In this case, we have a vertical directrix that is to the left of the pole. And we get this polar equation. If the vertical directrix is to the right of the pole, then the corresponding polar equation will be R equal to ED dividing by 1 plus E cosine of theta. If we have a horizontal directrix below the pole, then the corresponding polar equation will be R equal to ED dividing by 1 minus E sine of theta. If we have a horizontal directrix above the pole, then the corresponding polar equation will be R equal to ET dividing by 1 plus sine of theta. And for this example, we have the directrix at x equal to negative 10. E is set at 0.6, so the distance from the focus or the pole. So here's the pole. The distance from here to here is 10. And therefore the equation for this ellipse will be 0.6 times 10, which is E times D, dividing by 1 minus E times cosine of theta. And here's x equal to negative 9 for the directrix, x equal to negative 8, negative 7, negative 6, negative 5, negative 4, negative 1, negative 2, negative 1. Here we have the directrix to the right of the pole. So the equation will be 0.6 times 10, because the distance from here to here is 10, dividing by 1 plus 0.6, which is E cosine of theta. And here's x equal to 9, the directrix, x equal to 8, x equal to 7, x equal to 6, x equal to 5, 4, 3, 2, 1. Here we have the pole above the directrix of y equal to negative 10. The distance from the pole to the directrix is 10. And so the equation will be 0.6, which is E times 10 divided by 1 minus 0.6 times sine of theta. Here's y equal to negative 9, y equal to negative 8, y equal to negative 7, y equal to negative 6, negative 5, negative 4, negative 3, negative 2, negative 1. Here we have the pole below the horizontal directrix. The distance from the directrix to the pole is 10. E is set at 0.6. So the equation for this ellipse will be 0.6 times 10 dividing by 1 plus 0.6, which is E times sine of theta. And so here's y equal to 9, 8, 7, 6, 5, 4, 3, 2, 1. So in summary, if we have a vertical directrix that is to the left of the pole, then the equation will be R equal to ED dividing by 1 minus E times cosine of theta. If we have a vertical directrix that is to the right of the pole, then the equation for the ellipse will be R equal to ED dividing by 1 plus E cosine of theta. if we have a directrix that is below the pole, a horizontal directrix below the pole, then the equation will be r, the equation for the ellipse will be r equal to eg dividing by 1 minus e sine of theta. And in the last case, if we have the directrix, horizontal directrix, that is above the pole, then the equation for the ellipse will be r equal to eg dividing by 1 plus e sine of theta. And that's the end of the video.